Welcome and good morning to the conference opening of iiWAS and MoMM 2022. It is now the 28th of November. It is Vienna morning and it is other times all over the world. So not only a good morning, but also a good afternoon, and for some of you, maybe even already a good evening. As I said last year, we were truly hoping to have this event in person already this year, but unfortunately, when we had to decide on how to arrange and organize this conference, it was still too risky to have a physical meeting with international participation all over the world. So therefore, we decided to have iiWAS and MoMM once again as a virtual meeting, but we truly hope that this will be the last time and that next year we will meet again. And I can already announce that in the closing session, we will tell you the tentative place of the next conference. So let me start with today's opening session by introducing you the team of organizers and by saying hello to the organizers. And I would like to ask all of them who are present when I call their names to turn on the camera so that we can see each other and maybe you just say a hi. So the first one is Professor Ismail Khalil, the founder of iiWAS and also the steering committee chair. Hi, Ismail. Then we have Professor Sofian Chachayaputra from University's Islam Negeri, Indonesia. Welcome also, Sofian. I hope you're doing well over there. We have Professor Dirk Draheim from Tallinn University of Technology in Estonia. Welcome, Dirk, again in the virtual space. We have our General Secretary, Hesti Suchana from the iiWAS organization. Hello, Hesti. We have our Communications Chair, Paul Wiesinger, who is also taking care of all the technical details about this meeting. And on that occasion, I would like to mention that we are also streaming this session on YouTube and that this session also, therefore, will be public viewable by all the others. Then we have our proceedings chair for many years, Dr. Matthias Steinbauer. Also welcome to Matthias and thanks again for working with us. And last but not least, a warm welcome from myself, the General Conference Chair, Gabriele Kotsis. I would like to start in this opening session with a quick overview about the program. We are now on Monday in the opening session. Please note that all the timings are Vienna time and you use your preferred tools of calculating the time differences to your specific time zone. Right after the opening session, without a break, we are going to continue with the keynote at 9 o'clock. Then we are going to have half an hour break. For us, it would be a coffee break. And then we have the parallel sessions for the conferences. We have 2 parallel tracks for iiWAS and 1 parallel track for MoMM. Then we have another break, which will be 1 hour. This will allow you to maybe take some food. For us, again, it will be a lunch break. And then in the afternoon today, we will continue with another 3 tracks of the conferences, 2 for iiWAS and 1 for MoMM. And we will also have the World ABC Forum. I will come back to this in a minute. Tuesday and Wednesday have a very similar schedule. We always start first with the keynote talk, which will last 1 hour, followed by a short break. Then we have the parallel sessions, followed by a longer break. And then again on Tuesday, 2 more parallel sessions in the afternoon. And on Wednesday, please take a note at noon Vienna time. This is an important session. Here we are going to announce the Best Paper Award and we are going to do the closing. And as I said, we're also going to tell you some details about our plans for the next year's conference for iiWAS and MoMM 2023. Because one thing is for sure, although we are all pretty much used in meeting in the virtual space right now, it will be important that we continue this conference also in a physical format. And this is what we are going to hope next year. And most likely it also will be a hybrid format, but more will follow then in the closing session, as I have just announced. So this would be the program overview. I would like also to give you a little bit of a teaser about some of our program highlights. The first highlight will be our first keynote today on embedded machine learning for data quality enhancement in smart systems. The keynote will be given by Professor Antonio Liotta from the Faculty of Computer Science at the Free University of Bozen-Bolzano. And Antonio is a renowned expert in the field of machine learning, specifically machine learning on small devices, embedded machine learning, and he has authored several papers and is also the editor of one of the dominant journals in this field. So we are really looking forward here to an expert enlightening us about this new and important field of research. Another keynote will be given on Tuesday morning on data integration, cleaning, and the data application, research versus reality. This keynote will be given by Robert Wembel, professor at the Poznan University of Technology in Poland. Also, Robert is a well-recognized researcher in the field of data integration, and he is also a very enlightening speaker. So I'm sure that you will enjoy also his talk on research versus reality, and he's really an expert in this field. Keynote number 3 will be given by Professor Antonio Liotta from Tallinn University of Technology in Estonia, and she's going to talk about Are Telepresence Robot Here to Stay? So Jannika is also with us. Thank you. Jannika is an expert in the field not only of robots, but she's also always trying to bring technology into the perspective of the real world. And so we're also looking forward to her insights. And I think, Jannika, you're probably not only giving the answer, but hopefully raising more questions that we can discuss then later on. And I'm really looking forward to this talk as well. Thank you very much. I've already briefly mentioned the ABC Forum, which stands for the World AI Big Data Convergence Forum. This forum is already held for the 2nd time together with iiWAS and MoMM. And the chair is Professor Kim Wong, distinguished professor and president of Gachon University. Professor Kim, I think you're already with us. Is this correct? Maybe you can turn on your video. At least you wanted to join the opening. I don't really have a full overview, unfortunately, of the many names that are already here. Okay, Professor, don't see him yet. So I'm going to briefly introduce the speaker of the World ABC Forum. The idea of the forum is that there are renowned experts in the field of AI and big data convergence, and they are going to give keynotes, but they will also have ample room of discussion among each other, but also with the audience. And this year's keynote speakers come from different disciplines, but also from different places over the world. So we are really looking forward to an inspiring discussion from different perspectives. Our speakers are David Tanya from Monash University, Professor Delir Haghighi from La Trobe University, Melbourne, Professor Okran Jeong from Gachon University, Professor Yong-Yoon An from Gachon University, Professor Jiawei Han from the University of Illinois at Urbana-Champaign, and Professor Sharad Mehrotra from the University of California, Irvine. So this will also be a very inspiring event today in the afternoon. Unfortunately for some of us, it will be already very late, but that's the disadvantage of working in the virtual space in different time zones. Nevertheless, I hope that you will be able to attend this ABC forum. So the next item on the agenda would be a little bit more details about the program co-chairs. And first we will start with details about iiWAS, and it is my pleasure to introduce Professor Maria Indravan from Monash University, Australia, and Professor Eric Pardede from La Trobe University, Australia. Eric, I think you're going to start. The floor is yours, and I'm going to switch your slides, okay?
Thanks, Gabby. Hello, everyone, and good morning for colleagues in Europe, and good evening for those of you who joined the sessions from far away from Australia, like myself. So I'm going to talk a little bit about the program for iiWAS2022. We're very happy for this year's. We still receive quite a good number of submissions. We have 88 submissions coming from 31 countries. And like usual, majority of papers come from Japan, but we also have increasing number of papers coming from Greece, India, United States, and we also have, as usual, a large number of submissions from Germany and Austria. After rigorous review process, we accepted 26 full papers and 25 short papers. That represents around 30% acceptance rate, which is quite reasonable acceptance rates for the conference these days. We're very happy that we can select good papers because of the collaborations and hard work of our program committee members. We have around 70 program committee members this year, coming from 20 countries. The top 5 countries where they come from are from Italy, Japan, United States, Australia, and Austria. And all of the papers receive around 86% of the papers receive 3 or 4 reviews, and around 13.6% have 2 reviews. So next slide, please. So the theme of iiWAS this year is collecting, processing, analyzing, and storing data and information to support human intelligence. And we're very happy to arrange strong sessions, around 13 sessions. Many papers still work in the area of business data and applications. We also have a large number of papers focusing on aspect of performance and optimizations for processing and analyzing data. There are still papers in the area that we consider are quite established, such as in ontology, semantic web, and recommendation systems. But of course, there are also papers in emerging areas, such as in virtual reality, augmented reality, IoT, and so on. So we really hope these sessions and these papers, you can enjoy all of these papers. And for this year is the first time we actually published our proceedings by Springer on the Lecture of Computer Science LNCS series. And you can actually go to LNCS website or go to iiWAS website. The link is already there. So it's already published online if you want to download your papers or download the whole proceedings. So before I pass it on to my colleagues, I would like to thank, on behalf of iiWAS, I would like to thank ETWAS organizers for helping us organizing this conference again. Of course, I would like to thank program committee members and last but not least, all the authors who submitted their good quality papers to this conference. And I pass it on to my colleagues, Pari, for MoMM2022.
Yes, thank you very much, Eric, and welcome, Pari. It is my pleasure to introduce you as the program chair of MoMM, and I think you're also going to give you a few highlights about the conference and some statistics.
Thank you, Gabby. Yes, hello, everyone. It's a great pleasure to be in your company for another successful year as the chair of MoMM's conference. This year, as previous years, we received great papers from all over the world. To be exact, we received 27 papers from 18 countries. And all these papers, they went through a vigorous review process as before. And as you see in the second table, almost 60% of the paper had 3 or 4 reviews, and with some even 5 reviews they had. And for that, we are extremely grateful to our PC members who have extensive knowledge of the research areas and provided very high quality and constructive feedback. And exactly, we had about 33 PC members from 18 countries, as you see. And these accepted papers. There are 8 full papers and 8 short papers, and it gives us an acceptance rate of 0.3, which, as Eric said, it's a very reasonable rate. And these accepted papers going to be presented during the conference throughout the 3 days. And the information, of course, is in the program in detail, but also in the next slide. Thank you. You can see that we have 4 sessions for MoMM, and the topic of the MoMM is the same as previous year, which we are focusing on how we can design and develop these AI-based and very novel technologies and solutions for social good, for making our world better. And these 4 sessions, as you see today, we have 2 sessions, tomorrow 1 and Wednesday another one, both morning sessions. And these papers, as Eric said, for the first time this year, they are published in our new publisher, Springer, and we are very excited and about this. This is the cover of it, and it looks great. And as Eric said, you can, refer to it and find your papers there. And before I finish, also, I want to thank all our authors, PC members, and all the conference organizers to bring us together for another great, successful year. And as Gabby said, we are really hoping that this is the last year for all virtual, and from next year we can see you in person. That we are really looking forward to. Thank you, Gabby. I hand over to you.
Yes, thank you very much, Pari. Although we are used and familiar with virtual conferences nowadays, I would like to say a few words about how we are planning to organize this year's event, this year's conference. So I would kindly ask you, and this is perfectly working at the moment, as I can see, to turn the video and audio off during the presentations, unless you are the presenter. Of course, when you are presenting and talking, we want you to have your video and audio switched on. And I do hope that "you are muted" will not be the most important or most prominent question during this conference. Actually, I can tell you, I'm just supervising a student. He's doing a practical work and he's trying to analyze the lip movements of Zoom meetings. And if a person is moving the lips and being muted, then he will try to program Zoom in a way that the person is automatically unmuted. I hope that I can show you the results maybe at the next year's conference, and I'm sure this will be a very helpful tool that all of us will need. If you want to ask questions or have some comments, please use the chat. You can also use the chat for all kinds of interactions. And maybe this would be a good opportunity for all of you to say hi via the chat. And if you want, you can say hi from wherever place in the world you are. Hi from Australia, hi from maybe your office, whatever place you would like. So please try using the chat right now and say hi to us so that we can see where our audience is from. And I will actually start with this, and I will say hi from Linz in the chat. Okay, so now it's starting. Hi from South Africa. Great, great, great. So we see all the great messages coming in. I hope that I don't have to emphasize this in a scientific community, but nevertheless, sometimes we may tend to be a little bit more harsh if we are in the virtual space. I would kindly ask you to be as polite and constructive in your comments as you would be and as you always have been in the real world, because it's really important for the speakers to receive valuable feedback for their work, either, as I said, via the chat, or then during the sessions, the session hosts will allow you in asking also questions by turning on your audio and video. Talking about session hosts, we have 2 different roles of people that will assist you in the meetings. We will have session hosts, which are organizers. They identify themselves as co-hosts, and they usually have as their avatar for the meeting the iiWAS logo, and they will call themselves iiWAS and MoMM organizer. So if you have technical problems, please contact those people. In addition to those, you will also see people with a co-host role who are either the chairs of the session. They will also identify themselves and will assist you, of course, in any kind of questions that you have regarding the contents of your session. And we will also assign all the speakers as co-hosts, because this will allow the speakers to easily share their screens. I just read in the chat, hi from Tunisia. I do hope that the weather is warmer in Tunisia, because today in Linz we had already -2 degrees Celsius. So it's winter here in Linz. Having said this, these would be the technical things that I would like to tell you. Unfortunately, I cannot tell you any details about the coffee breaks, the lunch, the social events, because everything on that is on your own. But I do hope that you will use those 3 days in a fruitful way, that you will find time for virtual discussions, that you will find time to think about the new research work that you have learned during the conference, and that it will be inspiring for your own future research work. With that, I would like already to conclude the opening talk or the opening session of iiWAS and MoMM. I would like to express my sincere thanks to all the conference chairs who did an excellent job in putting together an interesting program, together with the large number of PC members and reviewers. Pari and Eric have highlighted how important their work is, and it's really appreciated that you send your valuable comments to the papers. It even helps those authors whose papers are rejected, because they will get important comments on how to improve the paper and how to improve their research work. I would like to thank all authors for contributing to this conference, and I'm looking forward to inspiring presentations. And I would like also to thank all the other participants who will engage in the discussions of iiWAS and MoMM 2022. Last but not least, I would like to thank my organizing team of the iiWAS organization and of Johannes Kepler University in Linz in again hosting this conference in an excellent way. I do hope it will run as smoothly as the conferences have been running in the past years. I think that's all. Ismail, may I ask you as my co-chair if I forgot to say anything, or if we can close now this opening session? Did I forget anything?
No, you didn't.
Okay. Okay, good. Then thank you once again. This will actually give us 8 minutes break, because in a virtual meeting we should start exactly in time with the next session. So Antonio, please be prepared. You can already start sharing your slides for the keynote then. And for the others, I would like to thank you very much and see you again in 8 minutes. We stay in the same Zoom room. So all the plenary sessions will be held via this Zoom link that you have just entered now. So this will be the Zoom link for all the plenaries, for the keynotes, and also for the closing session. And then for the individual tracks, you will find the individual links in the different programs. So with that, thank you very much. Antonio, maybe you can stay with me and already start sharing your screens. I will stop my screen sharing now. And I would like to thank you once again and wish you a very successful conference. Thank you very much. Goodbye.
Good morning, Gabriele. Please, you can test. Can you hear me? Oh, okay, fantastic. I'll try to share my screen. Yeah. Is it all visible? Okay, thank you.
Looks great. That's fine. Perfect. Yes, I think wonderful. Good. Okay, then I think you can already turn off your audio and video, and I will call you back when we start with the next session.
All right.
I will do a short introduction of yourself, and then you will start. Okay?
Right.
Okay, wonderful. I'm looking forward to that. Welcome and greetings to all of you all over the world listening to our iiWAS and MoMM conference this year. It is my great pleasure to introduce our first keynote speaker, Professor Antonio Liotta from the Faculty of Computer Science at the Free University of Bolzano in Italy. Professor Liotta is a renowned expert in the fields of data science and machine learning. He especially has been focusing on machine learning on small devices, on embedded devices, investigating techniques to micro-edge intelligence and miniaturized machine learning. Those kind of topics are intrinsically important for building the next generation of systems, for building smart cities, cyber-physical systems, the Internet of Things, smart energy, and related topics. Those are all fields in which Antonio Liotta is an expert, and he is also the editor-in-chief of the Springer Internet of Things book series that maybe some of you know and enjoy reading. It's a very prestigious outlet for publications in the field of Internet of Things. Antonio is also internationally very active. He has been the founding director of the Data Science Research Center at the University of Derby, and he's also actively engaged in setting up several cross-border teams, also virtual teams, and his publication record is truly impressive with over 350 publications and a lot of co-authorships showing that he is not only working on IoT and network systems, but he himself is very well networked in his research. So I'm truly looking forward to today's talk of Antonio. And I think, Antonio, you're going to introduce the topic by yourself, so I'm not going to read the title of your talk, but I will hand over to you now. Thank you very much. I'm really grateful that you're here for our first keynote of this year's conference.
Yes, hello everybody. Thank you very much for your introduction and welcoming also after so many years back to this conference. So today I would like to entertain you sharing some of my experience and lessons learned through a number of projects in this area of machine learning applied to the Internet of Things and then naturally to smart systems. Of which Internet of Things is an essential component, but clearly smart systems have many more components than just the Internet of Things. So let's see what, just a quick overview of what I'd like to speak about in the next 50 minutes or so. So it's really lessons learned, as I was saying, sharing with you some lessons learned so that hopefully this will spark some interest and some questions. But first, I will say a little bit what I mean by smart system, because that gets me into saying what's peculiar, what's so interesting from the big data point of view in smart systems. And then I'll quickly move into the key element that I think it's the key element of smart systems from the machine learning point of view is the issue of data quality. So I will talk about this and give examples of issues, problems, and solutions. And in fact, then I will go through some pilot studies and some field studies in this area, where I'll show how machine learning may be used to improve the quality of the data before you build those machine learning models. So I'll finish with some example projects. I'll see how many of those I can cover within the time I have. So what is a smart system? It's obviously everybody kind of knows what it is, but what I really mean to focus on is these elements that you have here on the left-hand side. So it's anything connected. So you have a network and then you're connecting pretty much anything, including sensors, obviously, but also actuators. So it's bi-directional. It's not just about sensing the world, but it's also about affecting the world. And one thing that I find also important to say, that a smart system has humans in the loop. So it's not just machines and robots and sensors and actuators, but there's humans in the loop. For example, think about a smart city, where obviously the target of the smart system is to improve the quality of living of humans. So feedback from humans is quite important, but also ability to positively influence the citizen into the smart city. That's why when we analyze data or big data, we not only have objective information, so coming from sensors, but also traffic, all sort of sites, but also subjective information. I will give you one example of where the fusion of such objective and subjective data becomes quite a difficult problem to manage, an interesting one from the machine learning point of view. And then all of that is about controlling, optimizing the system. And here we have different type of models. So, in a smart system, the main component, if I want to summarize everything in one slide, is the hardware, is the data, and is the machine learning. But when it comes to machine learning, then you see here we have the possibility of using conventional control theory and data-driven methods. And obviously, the conventional control theory is excluded because of the complexity. It's very hard to get a model of such a complex system. So we're only left with data-driven models, or AI, or different AI approaches, of course, not just machine learning, but other AI approaches. But we are ruling out opportunity to use conventional control theory, unfortunately, because it would be very useful, of course, to be able, if we had a model of the physical world, to be able to control it optimally. So we are left with machine learning in the end. That's what I will be talking about. So we are dealing with data-driven artificial intelligence. So not those models, but these kind of models with artificial neural networks and whatnot. And it is about building, data-driven is about building models based on data. So using our data, historic data and big data to be able to build optimizers, controllers, and making decisions using these models. What I'd like to argue here is that if we have to deal with smart systems and Internet of Things in particular, this is not enough, because the big challenges come from the ability to gaining new insights about the systems. So trying to find new insights, new patterns, to discover particular elements or particular behavior or opportunities for improving the system. And the other aspect, quite difficult, quite challenging and important, is the ability to use machine learning, so those data-driven models, to improve the data itself. Because one of the problems that we need to deal with in smart systems is the lack of quality in the data. So in this context of smart systems, we're dealing with complex enough systems. And the benefit of data-driven models or machine learning models is that these are typically more robust and more adaptive to changes than the physical model. So not only we are not able to build physical models, but we can build models that are more robust to changes, and we can use them to monitor and manage the system. But what's so peculiar, as I mentioned at the beginning, in smart systems, machine learning becomes peculiar. Well, these are some elements that are quite peculiar. First of all, the fact that we have to embed machine learning, so we have to use machine learning models in dumb devices. So typically, smart systems come from dumb systems with lots of hardware interconnected, and we want to smartify that. What we mean is to include some smartness in each of those hardware devices. The other aspect is that the data is not in one point, so we have to do distributed machine learning. A third element that makes it then quite peculiar, quite challenging, is that the data is typically of poor quality. So there's lots of gaps, lots of errors. So we're trying to build models based on data that has gaps, errors, noise, and whatnot. So the element of using machine learning for improving the quality becomes quite important. Of course, this problem is in any data science project, but in many data science projects, you start from a clean data set. So you see all those problems have been addressed before, and you can focus on advanced machine learning. While here you have to start dealing with the poorness of data, low quality of data. The other aspect is that you have lots of data. This again, like a big data, typical big data problem, but lots of data coming and being generated continuously in real time from different sources. But most of this data is not useful. So lots of it is irrelevant. And as you know, if you're working on big data, you're trying to look interesting patterns into a sea of irrelevant data, that makes the problem quite difficult to solve. And lots of data is also hard to correlate, because data is all the data are uncurated. They're coming from sources that are technically challenged by the weather, if you're collecting weather information, and similar problems you see in real life. So your data is generating in real life applications, and there's no opportunity to clean it and curate it properly before you get into the next stages of machine learning. It's a real-time problem. All the time, it's always a real-time problem. Of course, you can do post-processing, post-collection models offline, but a lot of interesting application come from real-time machine learning, and it has to be done at the edge. So it has to start at the edge. So that's the other element, that we can't afford working on the heavy computing, on the high performance computing only. Of course, that stays there, and everything eventually ends up collected into supercomputers, into the cloud for post-processing. But a lot of processing starts already at collection point, for example, in the sensors, and some examples I will give you in a minute in this area. So just to summarize what I said so far, is the smart systems are about the quality of the data as much as, of course, as they are quality of the models. So this is what we typically want. We want to have machine learning models that are as accurate as possible, but we bump into problem of quality here. So we also need to use machine learning to enhance this quality in real time as we are collecting. And I will give you some examples of precisely that domain where we're using machine learning to kind of curate the data in real time. So these are textbook material, just to show you some, for those of you who are less familiar perhaps with machine learning, some types of data-driven models that you can build. These are not the only ones. So you can have clustering methods to understand the system, to make sense of a system. So to extract new patterns, for example, to discover new behavior. Smart city is a good example where you can think of where you can try and discover peculiarity in the use of the city, or points where there's particular correlations of events and pollution, for example. There is another sort of machine learning methods that are about classification, where you try to categorize different events. So distinguishing, this is a binary example, where distinguish the reds from the blues. And you can use also, you can do time series analysis, in space and in time, with multiple time series, of course, at the same time. So this is a typical regression that's used for predictions. So here's an example where we are clustering data. Again, this is textbook material, so it's not just for smart systems, but then it becomes quite challenging when you project this kind of methods, clustering methods, into IoT systems, where you go from not knowing anything much about the data into having labels, so having more knowledge, so clustering by similarity and distances. There are examples where this is not so simple, like in this case, where clustering is not just an easy division of by distance, but you need to use more advanced methods, hierarchical methods to cluster and to find patterns in your data. That is just an example. To find the different colors in those data, it's not straightforward. It needs to be done through iteration, and it takes a lot of computing. So some of these things cannot be done at the edge, obviously. Here is a second type of machine learning models. It's to categorize events or classifiers. You go from a simplest possible situation where you try to find the best line that separates those two data sets, onto a situation where there is no curve that can easily separate two type of events. So you cannot use linear or any form of polynomial or more complex curves to divide the reds from the yellows, because these are divided through more complex shapes, and this happens of course in n dimensions. And these are just simple textbook example just to show you that this is not a simple problem. Sometimes it becomes quite difficult to find patterns. And going finally to the example of temporal data, that becomes very complex when you analyze multiple sources. In the Internet of Things, you don't have just a temporal data from one type of sensors. You have multiple, and that what makes it interesting is that you're trying to find correlation on patterns and making prediction where you're using heterogeneous data coming from, I don't know, traffic and weather and pollution and temperatures and so forth in the city, which also have the space dimension. So you're adding, you're working on multiple dimensions. So the pipeline for artificial intelligence, of course, is about building models. So starting from raw data, you want to make insights and understanding of the system and being able to model and predict the system. But what's in the middle, it's a lot of data science steps that typically starts from raw data. Then you're doing all this, the blue part is all the cleaning, curation of your data before you can think of modeling or building any of the models. Some example I've just given you in the previous slides. So the bit that we need to, that becomes peculiar is this blue part, because it has to be done mostly in real time as the data are being collected. And these are the typical V's that well, many people discuss. Of course, when we talk about big data, there are all the V's, the volume, the amount of data, the variety. You know, these are the typical examples used in big data. The one I want to focus here is variability, because in smart system that becomes quite challenging. The fact that you have rare events that are very hard to detect because they are rare. So in a machine learning model, you typically want to have many examples of some event before you can model the way to detect those. But the rare events are what the word is saying, because they are rare, they're difficult to model and detect. Same goes for anomalies and outliers and errors. So being able to distinguish between something that is because of a collection error from an anomaly that comes from a real physical anomaly is very hard to do in smart systems, where also the time series, for example, they typically they're sampled at different frequencies. So you need to compare things that are collected under completely different physical conditions. And of course, there's all sorts of other problems with the velocity of data. They're all shared with big data problems. The key that I want to point to is that managing all these V's, so all this complexity, requires specific methods. And you cannot just manage all those V's by using powerful computer clusters. You need specific methods, and those specific methods start at the collection point. So here's a simple example, for example, where you're trying to make some analysis of something happening in a city. So this could be mobility traces, or could be pollution over time. So you have space and time. And the point here that because the quality of this data, so that the confidence in the quality is typically low, because the collection points are not fully maintained, and they are prone to collection errors. It's very hard to think about modeling such events and complex events to try and understand, for example, like in this case, spotting the dark spots where the pollution or congestion takes place. Is hard, if not incorrect, to try and build those models before you make sure you improve the quality, because you have lots of uncertainty in the data. The other problem that you typically face is that you hardly have statistical significance in the data, as much statistical significance as you would like to have, because all data are sampled. So here, what you see is somehow correlation of events that are based on samples in space and time. So for example, you see here, there's not much sampling in those areas at the edges. Most sampling takes place here, but there are samples, there are sampling stations, so you don't have exact information. And the same happens in time. Information is collected, it's sampled with a given frequency. So the problem of improving quality through fusion and transformation and machine learning models before you build any of those models becomes paramount importance. And the other thing that we notice when we study those traces is that there is lots of opportunities for sloppiness at all stages. So you could see situation where the collection of data has not been done properly or is not statistically significant. So we build models based on data that are not statistically sufficient. So the pre-processing, the transformation of data is often not done properly. So again, all these stages in data science that are so important and typically are done offline by experts, they need to be done together with the collection of the data. The other problems that we see is that quite often machine learning is used as a black box. So the tuning of a black box without having knowledge from the problem domain is often a problem in terms of being able to interpret those data, those models. So the explanation is quite problematic a lot of the times, unless we open this black box of machine learning and try to add explainability to the models. Okay, so these are obviously big chapters in data science. So those of you who have been involved in big data, data science, machine learning, we are perfectly aware that data cleaning, data enhancement, data transformation are very big chapters. But in the case of smart system and intelligent Internet of Things, so these dedummified systems that we connect, they become new chapters in data science, because all those elements that are typical and textbook material, where you start from raw data that comes from probes in this case, and then you start exploring, cleaning, transforming, changing, and doing feature engineering, for example, all these things become quite new when it comes to smart systems. So I'll give you some examples that are typical and standard in machine learning, and so that you can appreciate how those things become difficult and peculiar in smart systems. So these are the typical transformation of data that you do before you think of any machine learning, and I'll give you some quick examples in a minute. So data aggregation, sampling, subsampling, discretization, transforming the attributes, transforming the features, reducing the dimensionality, so the features, and all sort of feature engineering, and all. I want to show through some example how all of these elements become quite challenging in smart systems. So this is something that we have become accustomed in the past couple of years, where we were looking at daily figures, but in fact, what we were looking at more interesting was this curve that was built on over the daily figures of different cases, coronavirus cases. The 7-day rolling average it was not there just to add extra curves to the data, but because obviously when you're aggregating the data, you're filtering out the noise, the errors, collection errors. All these spikes were due to collection errors on some days. And if you want to build a prediction model, which was the important case for this example, you don't typically use the prediction models directly on the raw data, on the daily figures, but you want to kind of have a more regular curves before you do it. So these curves are there to make an easier explanation of what's happening, of the physical phenomenon happening behind the data, but it's also as an important pre-step before you start trying to build prediction models. This is another example of sampling that a lot of the times we have to do in a smart system. We do have to continually make decisions as to how to filter and reduce the complexity of data, because you just have too much data. So if you have some data and you're trying to spot a pattern, the typical thing is that you have to do is to spot the very same pattern on a subsample of the data. But if you subsample too much and if you go too far, then you lose the pattern. So the other critical aspects of this is those trade-offs analysis. When you have all these samples, for example, temporal series at different frequencies, you're reducing the frequency to be able to subsample. You need to establish, and you need to find automated ways to subsample without overdoing it. Otherwise, you lose the pattern. So you see, you lose your ability to detect the meaning out of data if you subsample too far. But if you don't subsample, like in the original case, you may not be able to process the data in real time, or you may not have enough ability, not just because of compute power or availability of memory, but simply because if there's too much data, computing all those patterns and distances may become a very complex problem that you can't solve with extra computing. You just need to subsample. So subsampling becomes very important. Discretization is another well-known technique that is used. So you're going from beans that may be too narrow, and you can start discretizing your data. You may go into beans that are too wide. So you need to find somewhere in between that allows you to do whatever analysis and modeling that you need to do. The other aspect that's one of the curse of dimensionality in machine learning is the fact you have too many features. For example, if you're doing imaging and you treat each pixel as a separate feature, and then you can extend that to video, then imagine high resolution images, you have millions of pixels, then it becomes impossible to do any machine learning. So you typically extract features before you do your machine learning on the features. Now, this is a classical example where you have the quite famous digit recognition data set that is used for benchmarking most typically, where you have just 64 pixels per digit is 110 digits. There's some subsampled, and I'm sure that you can, with your naked eye, recognize most of those digits in spite of being very low quality. But now what we can do is to train, so to build new features, so to try and represent the very same data set from 64 dimensions into 2 dimensions. So you can just have 2 components, these 2 principal components, and then you can represent the whole data points in this data set with those different colors and positions. So this data set can be represented in 2 dimensions. And of course, here you can distinguish certain digits. For example, this digit 0 is quite distinct compared to digit 1. So you can see they are far away in this 2-dimensional feature space, but other digits are mixed up, and it's very hard to build a classifier that distinguishes all those 10 digits from 0 to 9 if you're working in 2 dimensions. That shows you that how sometimes you need to transform your data from one complex domain into a simpler domain. Sometimes you can do it successfully, sometimes you can't. So if you want to distinguish between zeros and ones, this transformation would be good enough. But if you want to distinguish all 10 different digits here, then you need other methods. But the principal component analysis is a classical example as to how you can simplify the dimensionality of a machine learning problem. And sometimes you need to do this in real time for IoT, and it becomes even more challenging. Here, another classical problem that made laugh a lot of people is the debiasing. So it's quite easy to get biased data. And then if you start building your models on biased data, what happens is that you transform Barack Obama into a white person simply because the model to depixelize those images were built on white male people. So you can depixelize a low quality image and reconstruct a high quality image, but you end up with somebody else, not because the machine learning model is incorrect, but because it's based on biased data. So that becomes even more challenging if you try to debias data in real time. So I'm trying to give you examples that are quite well recognized in data science and machine learning, and just think about how those problems can be solved when you have plenty of time and compute power, but how difficult, more challenging this becomes when you are dealing with real-time smart systems. Now I would like to give you some examples, in it's a little bit more time, examples of projects and pilot studies that I've done with my collaborators to see how far we can try and solve some of those problems that I described in the first half of my talk. So how to use machine learning, data-driven machine learning models, for example, for imputation of missing values. This is quite a big problem in IoT and smart systems in general, because missing data is this is a typical data science problem, becomes quite harsh in the context of smart systems. There is an example of techniques that we published recently, where you just take a nice and well curated data set. This is environmental, so pollution. So obviously, as a environmental pollution data set is less challenging than other data sets because of the regularity of how pollution is changing, the inertia behind pollution. I mean, typically those values like ozone levels and monoxide, carbon monoxide, and all that, those values don't change every nanosecond. There is some regularity. So it's obviously quite slightly easier to tackle some of the problems. So we take a nice and clean data set, then we start polluting, can change, affect put gaps, put holes in the data set through some different randomized techniques. And then what we do, we try and see if we can do that imputation, so correct the errors in real time with Raspberry Pi, small computers, so that next to the collection point. So you can set these small computers, mini computers, next to the sensors and see how far you can correct those errors or gaps and noise in real time, so that you effectively do data cleaning in real time. So what happens is you can try different methods. These are different colors are for different methods that we used. All of this, we tried those in to do those things in real time in small computers, in laptops and Raspberry Pis. So what you see here is the increasing level of contamination, so gaps that you plug randomly into nice and clean data sets. So you start from a nice and clean data set, then you start putting 20, 40, and 60% of error or of gaps. And here you see you measure the error in a simple way, and the different colors are showing different machine learning methods. They're all quite simple. So you start from statistical methods like mice, and you can go to simple KNN imputation, where effectively you replace all the gaps, all the missing values with the mean of the nearest neighbors. But you need to do some tuning, some trade-off tuning, so that this can be done in real time and at the edge. So if you look at all the curves, the error that you obtain after you do that imputation with simple methods jumps up obviously quite quickly. And as soon as you start using KNN and decision trees, then you can keep the good tab with the errors. You can keep the error quite low. So in this case example, up to 55% of gaps can be imputed, can be corrected with kind of a 10% error, which is quite a good example. But of course, root mean square error is not the only measure, is not the best measure to check that you've done a good job at reconstructing your time series. So you can look at density distribution of our samples, and you can see this is an example where we plug 50% of holes in the data set. So we do contamination of 50%, and the original data set is the blue color that you can hardly see here, because the brown distribution of the data set that's been reconstructed. So all the errors have been corrected, where we not only have, like in previous case, low error, but also the distribution of the data set is correctly reflecting the original distribution. So that the brown and the original, the blue curves are indistinguishable, because they are kind of, the reconstruction is almost perfect. So this can be done in real time. And the point is that I wanted to make is that how important it is to use this simple, and even we can get even more complex, even neural networks to do those correction of errors in real time. Now I get into some prototypes that we have gradually built, that maybe can demonstrate some of these aspects in more detail. The first one is some measurements on precisely the simple example I just described, where you have we measured this data imputation, real-time data imputation on laptops and on Raspberry Pis. And then we have different types of errors, some random errors that you were plugging high percentage, up to very high percentage of gaps into the data set. But we also tried, and didn't show you the plots, bursty errors that are typically that happens when you have communication problems. So if all of a sudden there is an interference from a sensor and you lose a train of measurements, you don't just lose one, that's where the problem becomes really challenging, because trying to reconstruct a train of errors is much more challenging. And here you see different methods, just pointing at the green part. So using KNN, the KNN method, you can, with Raspberry Pi, go to 10 of seconds, you can reconstruct the errors in real time. So obviously, if you're sampling at frequencies that are higher than that, it's hard to do. So you cannot do it in real time, right? But the difference between having a laptop, kind of state-of-the-art laptop, you can correct the errors in about 2 seconds, and then you need about 15 seconds to correct the errors with a Raspberry Pi. That is more realistically, that's sort of computer you can place next to a cluster of sensors, for example. So if you are sampling a 15 seconds periods, then you can correct the errors immediately without any further action. Here's another prototype of a completely different problem, where we're trying to do anomaly detection in real time without programming the anomalies, without specifying the anomalies, and using some machine learning on directly on the sensor, so without even connecting next to the sensor a mini computer. This is a sensor with about 48 kilobytes of RAM. Kilobytes, I'm not saying, there's not a mistake, no megabytes, kilobytes of RAM, and you're trying to somehow find anomalies, spotting anomalies in the measurements. So you have, in this case, you have 3 sensors, optical sensors and temperatures. And what we can do, if you can tap on the sensors, effectively what's happening is that we are measuring different values for luminance. And then these are different methods. These are shallow machine learning. Obviously, you cannot use artificial neural networks on a 40 kilobytes RAM device, but you can imagine extending these two neural networks, simple neural networks like sparse neural networks, where you can do something similar with neural networks. And here, what you do without programming, without specifying how the signal is, the time series in this case, the time series, the shape of the time series, the system can be trained looking at a small windows, observing small windows of measurements, can be trained to understand the normality of a signal, so a normal time series, and then detect an abnormality immediately. So I just try to run this video, see if I can run it. Okay, so here is you at the beginning, you're self-calibrating machine learning methods. You see a red flashing LED here, and at some point there's a convergence. The system converges to understanding that this is the typical time series based on patterns, simple tapping patterns. And then if you stop tapping, then it's flagging, the system is flagging as an anomaly. And if you go back to the same pattern, it's remembering the pattern, so it's going back. So it's kind of dynamically reprogramming the anomaly detection system. Anomaly detection at the edge is very important, not just for this kind of little game that I've just shown you, but because through anomaly detection, or you can distinguish between rare events, detect rare events, which are typically the ones that you will want to study into the cloud. And you can also filter out normal events. For example, this tapping, continuous tapping, if that is the normal events, you don't need to transmit all those events and only transmit the anomalous information down into the cloud for further analysis. So anomaly detection at the edge is quite important for rare event analysis and for reducing the redundancy that you typically have in data. Here is the last example of a prototype that we built a few years back, where there's a different problem. We are using this case reinforcement learning. So it's Q-learning was the implementation in this case. Q-learning running on this device, and you can see, I mean, I will leave the slides obviously, so you can see all the pointers and all the papers where you can find all the data sets and more details. So you have a simple mini computer here, and the problem would be how this is transmitting and receiving in a context where other devices are transmitting and receiving. So there's interference, and the problem as to which transmission power you should use is quite difficult to solve with conventional methods. And in this case, we're using Q-learning, so reinforcement learning, to find the minimum transmission power. Minimum, by minimum, we mean the one that is minimizing interference and is maximizing the transmission rate. Okay, so here you have epochs over the time, and you are transmitting at different transmission power. Imagine that these Q values are kind of linked to transmission power. You are changing the transmission power over the time randomly until the systems, through reinforcement learning, learns how the exact transmission power that in that given time is optimizing the system. So you're kind of, if you imagine that you're running the same algorithm on similar devices that are running nearby each other, and you have a system that can self-tune to minimum transmission power, to minimum energy. In fact, you were to measure the battery lifetime for this device could go up by 10 to 20 days compared to a system without this self-tuning. Okay, so you have seen here diverse examples, starting from this one where we're doing data imputation in real time to anomaly detection in real time at the sensor, and this other where you're doing transmission, so energy minimization in real time at the edge, using different types of machine learning methods, from KNN into simple shallow learning, into Q-learning, reinforcement learning. These are just 3 examples, and you'll see the papers with all the details. Please get in touch, of course, if you are interested in having more information. Now, I wanted to use a little bit more time to discuss a couple of pilot studies. So these not just simple prototypes like the ones I've shown you before, but pilots done in a real environment with European projects. We're trying to correct errors to address some of these data quality issues before we do the machine learning. One example is was again done during COVID times, I'm afraid. So there was an opportunity to study data during that period. And this is a map of high touristic city in Italy, in Cagliari, in Sardinia. And the problem, of course, is that everything stopped during COVID time due to lockdowns. So we had an opportunity during that time to analyze mobility traces through a system that had been deployed before COVID. So we have historic data of car mobilities, different car mobility across the city, dated as far as 2016. And then the system kept on working during COVID times, where, of course, the mobility patterns changed dramatically. And this was the ability to, the aim was to try and measure the bit of a city. So what is the minimum mobility patterns that you have to have in a city, even though everything else has stopped? So it was quite interesting research question, except that we couldn't answer this question immediately, because we immediately bumped into another problem. And the problem was that the mobility traces coming from the systems fairly quickly appear to be incorrect. So you had measurements that were anomalous, but were anomalous not because of COVID, were anomalous because of 2 reasons. One reason was that there were collection errors, and the other reason is that there were also anomalies. So the 2 anomalies had to be distinguished. We had to do data imputation in quite a complex environment, because we had a special temporal data series with missing data, with incorrect data, and with anomalous data, all mixed up together. So that made it a perfect storm for a data science project. So these were if you want to visualize the traces, all the white areas are gaps where the data was not transmitted correctly. So imagine a system where you, over the time, you have lots of data transmitted from different sensors. I mean, here there's kind of 1,200 sensors across the city. Although this is a small city, you still need lots of sensors to subsample. You only have samples in a small portion of the city center. And you have lots of gaps, so the white parts, but the gaps are not really the problem because it's quite easy to do that imputation on those gaps. What is the problem is not the gaps, is the incorrect measurements. And if we just, this was from one sensor, just to give you an impression of the kind of problem that you had to solve when you're collecting data in real time. These are the measurements. And this period that you see here, this is during Easter time, you see an interruption of movement, and you see values that are extremely high. If I go there and zoom in this part, in fact, this was taking place during Easter Sunday. It was total lockdown at that period, I'm afraid. So the problem there that you see this anomalous traffic, there is traffic that goes way beyond the physical possibility of traffic. I mean, going at 300 kilometers an hour in a pedestrian area, it's physically impossible. So obviously this information is incorrect. And at the same time, this is happening where there's supposed to be no traffic or virtually no traffic in a city. So how to distinguish, how to detect these errors in the measurements from the anomalous behavior? Well, if you're using some machine learning, so you can simply do time series analysis and see that the data doesn't make sense, and it doesn't make sense because of those errors. So the data doesn't make sense, the trends analysis is incorrect, the periodicity is incorrect at all levels. So we have weekly and daily periodicity that is completely incorrect, although we are dealing with exceptional situations. So you may expect that these strange anomalous patterns are due to restrictions, movement restrictions. In fact, you can then curate this data set and come out with periodicity that do make sense, and then analyze and compare those with pre-COVID time series. Okay, so this correction of data was done through machine learning. So that's a kind of a case for using machine learning to check the quality of your data before you use it to do any sort of studies, and then going back here and being able to check the mobility patterns. And this is a simple visualization, obviously, but can you imagine all sort of analysis that you can do, but you should only do those after you are confident about the quality of the data. Otherwise, all the strange patterns that you observe are due to a mix of collection errors and anomalous behavior, and you need to distinguish the two. So quite an interesting, I think, pilot study from that point of view. I can give you more information offline if you are interested. And the other pilot, I spent the last 5 minutes or so to go through another pilot, because I find it interesting, because here it's a smart city pilot where we had to do fusion of objective and subjective data. Remember what I mentioned at the very beginning, an interesting thing about smart system is that you have humans in the loop. So you need to be able to analyze subjective data together with objective, like sensory data, to make sense of a highly subsample data set, which is what you typically have in a smart city. So this was a well-being pilot, pre-COVID time, so no longer discussing those things. So we were trying to understand other aspect. We have a big pilot study with over 1,800 subjects being monitored. Their movements have been monitored for about a month, and we have geofences, and we had objective information coming from street maps, coming from sensors, coming from the smart city, and at the same time information, subjective feeling about citizens moving about the green areas in the city, to try and establish a number of things about the features in a city that make it more livable. Okay, you can address all sorts of questions about citizens. If you are in a smart city, you have a smart citizen with a mobile phone, so you can collect data automatically or explicitly, subjective data through humans, and you can fuse that together with objective information, except that, as you can see here, you have a snapshot of data that changes over time, but is highly subsampled. So although we had lots of subjects, it's quite uncommon to have so many subjects in a subject study. Typically, you don't have thousands, you have hundreds, maybe you have thousands, but because the space, the size of the city, it's very hard to get statistical significance of the information, subjective answers coming from citizens, which is statistically significant for every single area of the city. So we're trying to focus on portions of the city where data was highly, sufficiently concentrated, and try to gain statistical significance in certain areas, and in other areas, of course, you have to give up and say for those other areas there is not enough statistically significant information to draw any meaningful conclusion. So when we do work on smart cities, it's quite common to subsample and to draw conclusions, while it's in fact important to look at if you have enough data. And sometimes, and what we were doing here, one of the things that we were doing here is monitoring along the days, as the days of the pilot study passed, we could just run the subjective collection of subjective responses pretty much automatically, we could, so this is the blue line. So it's just randomly firing questions to the citizen as he or she was walking about the city and trying to establish their feeling about green features in the city. Or what we could do, fuse subjective data and try to fire those questions still randomly, but in a guided way, while they're firing the questionnaire into the mobile phone was guided through objective information that we were collecting in parallel. And if you look at the statistical significance of the sample, it goes much faster and you gain statistical significance. So you have enough answers for them to be statistically significant in a much shorter time. So kind of boosting up the subjective data collection by guiding it through objective information. And if we were not doing that, the data collection would last way longer before you could reach statistical significance. So you can imagine how boosting up this subjective study, in this case, means covering larger areas in your city way faster. Okay, then would like to mention a couple of research challenges, because so far I've talked about problems, I've talked about about projects, and some of the challenges that with my group and collaborators we're looking at are relating to how to do embedding machine learning. So that means miniaturizing machine learning so that you can do machine learning as complex as possible. So even going into artificial neural networks at the edge. So going into Raspberry Pis and then even into sensors. That means being able to miniaturize your learning training models so that they can, for example, through sparse neural networks. The other side of the same coin is to accelerate machine learning. So if you have big data pipelines and you can miniaturize machine learning, you can also accelerate using similar methods. You can also end up accelerating machine learning in computer clusters. So similar methods, and also doing a lot of work on edge machine learning, doing a lot of, for example, quality enhancement, and giving you some examples of quality enhancement that can be done at the edge, anomaly detection, filtering out irrelevant data, all of these done at the edge. These are some pointers to some papers where you can find more information, but the work I think is quite interesting after a few years of working in this sparsification of neural networks. So it's a highly theoretical problem which has an immediate application to edge machine learning and to machine learning acceleration. Is this scalable training of artificial networks? The idea is that you try and work using network science techniques, try and always train neural networks that are sparse. So you never train a fully connected neural networks, and that gives you an acceleration factor that makes a huge difference. And it allows you to have very small neural network models that you can embed into small devices quite easily. And then after we published this paper, quite shortly after that, 2018, somebody else took our code and they re-implemented, re-optimized, improved everything. And you can see all the pointers here. This is somebody else's paper authored in the States, where they they were benchmarking different types of data set. These are quite massive data set. They were benchmarking them with sparse neural networks. So this is a kind of our method that we proposed in 2018, and the conventional approach. So if you look at the number of neural links that you need to train, typically with fully connected neural networks, you go to into 10 to the power of 9 links that you need to train. Imagine doing that on a small device is impossible. But on the other hand, you could achieve exactly the same accuracy, in terms of accuracy of model, with a model that is has 10 to the power of 6 number of links, so 3 orders of magnitude smaller for different types of neural networks. So the reason why you see a frog here is because they made big news by training 1 million neuron multi-layer perceptron in a laptop without GPU. So they ran all those tests in a laptop without GPU and achieved the interesting performance. Now, there's a lot of things I haven't talked about, obviously, because of lack of time. So I come to an end of my presentation, but I will leave this presentation somewhere into the conference repository, so you can of course go there and check. There's a lot of implication when it comes to working on earth and climate monitoring and observation and studying. Of course, these are increasingly important topics. So there's a number of papers that I leave you for you to check. If you find anything interesting, get back to me. Working in collaboration, for example, with Shanghai Ocean University on earth and climate monitoring, on ice monitoring, ocean monitoring, on different water, rain. All these things are very complex spatial temporal series analysis that needs to be made. So neural network acceleration is quite an important element to these kind of problems. Push a neural network to their very edge. So there's a number of papers that you can see here, and I'd like to take 1 more minute to draw some conclusions, maybe point to the more elements, because I talk about a lot of things I wanted to share, as I said at the beginning, lessons learned more than going through a formal presentation. The first thing I would like to say is that AI models are, of course, as good as the data. This is obvious to any data scientist, any computer scientist. But in the case of smart systems, this becomes an obligation. There's no option to avoid that. So to clean and improve the quality of the data in real time and to a good extent is essential. Then this data-driven AI starts with data enhancement, cannot start directly with the data modeling. The aspect of models, AI models, maybe this is more of a message for those who are more from the application domains and more than from the computer science domain, because we do have to work with people from a medical domain, from climate domain, from different domains. And of course, they sometimes expect to have models that are accurate, but in fact, this is not what we are aiming at. We are aiming at models for which we know where the boundary of usability, we know the confidence of the prediction, but they're never 100% accurate. And that's not what we're striving for. We're not striving for accuracy. We're striving for confidence in the models. And the other aspect that I haven't talked about much is the fact that some models require explainability. So the AI black boxes can be used for system control, but sometimes you need also to be able to explain those models so that you can make new insights. By explaining models, you're making new insights into complex systems, so you can spot new patterns, for example, in a smart city. So I think the final message is that AI goes beyond the big data, because I've talked about, of course, big data, so you need lots of data to train your models. But in the case of smart systems, what you are actually interested in is the small data, so the rare events, and finding those rare events, those anomalies in a sea of data that is generated in time and space at high frequency is really challenging, because you need to filter out all the redundant data or the useless data before you can build the models to spot the small data. So it's more of a small data problem, in fact, using big data techniques. I think this is as far as I could go. Unfortunately, I don't have any more time for more examples. So let me thank you for listening. And the floor goes back to you, Gabriele.
Yes, thank you very much. I hope you can hear me because my Zoom client just crashed, so I had to move to another computer, but I'm back again.
Yes,
yes, thank you very much for your inspiring talk. Before I allow the audience for a couple of questions, I would have one question. You mentioned in your example where you were able to detect with machine learning the anomalies, and you said we realized that it doesn't make sense. But how do you teach this make sense to a machine? What exactly did you use there?
you're talking about the prototype on anomaly detection?
Exactly, yes.
Yeah, okay.
Yeah.
Yeah, these are just data series. So you have a series of,
Okay.
of course, if you know something about the origin. So if you're trying to train a temperature sensor is different from training a sensor with a different sort of inertia. So you need to have some inside knowledge and try to make use of that. But what you have a train of measurements, and you try detect the patterns. And as soon as you detect the pattern, then the system has been trained. And as soon as you see differences from the pattern, that's the anomalies you're looking for.
Yeah, but still you need to look into one very specific example, because what I truly believe would be maybe the next step in machine learning would be to have some more kind of world knowledge as we human beings have, because we know so many things, and all the things that you have presented are excellent examples, but they're again very specialized tools, right? And you can solve one problem in an excellent way, and human beings are still much better because we have this broad perspective. So do you think that AI will also go in this direction to have a more broad understanding of the world?
Yeah, I mean, I like this question because it's exactly the point. So what I discussed today in a way is the engineering part, not the human part of intelligence that you can do at the edge. So the idea is that you can instrument the edge to be more automated, but then I would see what you're talking about, improving AI into more human-like decision-making. This is still a cloud-based domains. So of course, in a sense, so you are not trying to do anything more than analyzing your time series in a mathematical way. So you're trying to filter out useless data, but you're not trying to reason. So all the reasoning, all that semantic modeling, all that part, obviously, don't expect this to be done at the edge. So the idea is to use edge machine learning more. It becomes the simplest possible form. Simple by simple, I mean cognitively speaking, is the lower level of intelligence, which is more sensing than intelligence at the edge. And then as you go towards more powerful center or cloud or supercomputers, maybe there you can work. And you need to complement those two mechanisms. They're not independent. And that was what I was trying to argue, is that
we're also talking now
continuum.
About collaborative systems and things like that. Yes. Okay, so I would like to open the floor also to questions to the audience. You may either raise your hand and then turn your microphone on, or you ask your question in the chat if there are any questions or comments to our speaker. We would have some time to allow for some questions.
Of course, I'm also very happy to discuss offline later if people are interested in any of those things.
Great.
But
okay. Yes, I think, I don't see any online questions, so maybe let's thank our speaker very much with a big applause. Thank you very much.
Thank you.
And as you said, you will be able or will be available for us for later on discussions. And we will continue now in about half an hour with the parallel sessions. And please note that for the parallel sessions, you would need to use separate links. And maybe, Antonio, you would like, I'm going to keep this meeting open for maybe another 10 minutes. And maybe, Antonio, you will stay if somebody has an individual question for you in the chat. Okay?
Absolutely.
Very happy. Small coffee break. Good. Then thank you very much for this great introduction, and enjoy the rest of the talks. Thank you.